Alright, here we're doing a little walkthrough of the Chapter 8 test. I'm not going to go into great detail explaining every formula, but I will explain each question and which formulas you use for them. Of course, first of all, anytime you're doing trigonometry, you want to make sure you're in the right units in your calculator. You know, by default, it's set to radians, and so you're going to want to make sure you go to mode and change that to degrees for this whole test. Secondly, I'll be referring to all the formulas and steps on the flowchart that we made in class. Keep in mind that first question that you always ask is it a right triangle? And if it is, then you're looking to use Pythagorean Theorem, Trig Ratios, or the triangle sum theorem. If it's a right triangle, you might also check to see if it's a special right triangle, which will save you a lot of time. Of course, if it's not a right triangle, or if you can't determine whether it's a right triangle, then treat it as oblique and use either the law of cosines or law of sines. But remember, you don't want to use the law of sines to find an angle unless you absolutely have to. That is, unless you only have two sides and an angle not between them. In all other cases, to find an angle, either use the triangle sum theorem or the law of cosines inverse. Okay, with that out of the way, let's go over this test. As I just said, on the left side of that flowchart, you can tell, you want to ask if triangles are right first, and you can tell if they're right if they fulfill the Pythagorean theorem. So it's only 4 right triangles, and you can also use it to verify that a triangle is a right triangle. Isosceles right triangles, also known as 45, 45, 90 triangles, have a special ratio between hypotenuse and leg, which is the square root of 2. 30, 60, 90s are the other special right triangles, and the ratio between hypotenuse and the shortest leg, the one opposite the 30 degrees, is just regular 2. The sine of an acute angle is opposite over hypotenuse. You know that from Soh Cah Toa. Trig functions always take angles as their inputs. Inverse trig take sides or ratios of sides as their inputs. But trig functions take angles and they output ratios of sides. And then to solve oblique triangles, use the law of sines and cosines. A lot of students will try to always use the law of sines or cosines, but as I said at the beginning, those are really for solving obliques. The more appropriate tool, if you're looking at a right triangle, is trig ratios or Pythag. Okay, just checking that you know sine, cosine, and tangent. Remember, you always take the perspective of one of the acute angles. Here we're taking the perspective of theta, so 16 is the opposite from that. Opposite the right angle is always your hypotenuse, and the adjacent is the other side, the leg that touches the angle that you're taking the perspective of. So sine is opposite over hypotenuse, in this case 16 over 34. You can reduce this to 8/17 if you'd like. I don't need you to. Cosine is adjacent over hypotenuse, that's 30 over 34. And tangent is opposite over adjacent, that's 16 over 30. Of course, you could reduce all those, it doesn't matter. I'm just checking to see that you know the ratios, the correct sides to use. Okay, for 3 and 4, while you could do these with proportions, we use proportions to find this pattern of what we call a geometric mean, which is just a square root of a product. So the geometric mean of 15 and 6 is the square root of 15 times 6. And that's equal to the altitude. Always the case for right triangles. So yeah, just the square root of the product of the two parts of the hypotenuse. That is the square root of 90. And of course, I want you to be totally polite, fully simplified. So if you make a tree for 90, you'll see that it has branches of 9 and 10. And that's 3 and 3 and 2 and 5. So a pair of 3's and a 2 and a 5 left over. That makes it 3 root 10. The 2 and the 5 multiplying to make the 10. For number 4, well, some people do a Pythagorean theorem to get this altitude, and then they do that same formula. We really could just use the formula for one of the legs. It's the geometric mean of the part of the hypotenuse closest to it and the whole hypotenuse. Now on these problems, it's good to label the length of the whole hypotenuse if it's x units from here to here and 18 from there to the end of the hypotenuse, then the whole hypotenuse is x plus 18. Okay, so this leg, which we know is 20, equals the geometric mean, that's a square root of a product of the piece of the hypotenuse closest to it, 18, and the whole hypotenuse, x plus 18. And now we just solve this equation for x. You'll square both sides to get rid of your square root. Cancels out on that side, and you get 400 equals. And I'm going to distribute this 18 into the parentheses, so I get 18x plus 324. That's 18 times 18. And now we just subtract 324 from both sides and divide both sides by 18. That's 400 minus 324. And really, it's just 76 over 18. I don't want you to give me any rounded decimal. Of course, you should reduce that fraction if you can. And a reminder, if you ever struggle to reduce fractions, the calculator is really clever in that. You just divide the numbers and then hit math, enter, enter. We just math frac it, and it turns it into a reduced fraction. All right, now we're on to finding unknown measures of right or oblique triangles here. Don't have to solve the whole triangle. Here we're finding this side length. And I see 40 degrees and 102 degrees. If I know two of the angles, I know I can use the triangle sum theorem to find the last angle. That's just 180 minus 40 minus 102. So that last angle must measure 38 degrees. We use the triangle sum theorem. Triangle sum theorem. Okay, now that's 38. My largest angle is 102 degrees. So right off the bat, I know if this is the largest angle, there could not be a right angle on this triangle, because 102 plus a 90 degree would exceed the 180 allotted for the triangle sum theorem. Therefore, I know that I'm on this right side of the flowchart. I'm not dealing with the right triangle. I cannot use Pythag. I cannot use trig ratios. I have to use the law of cosines or sines. And looks like I've got angle side angle. That was my starting case here. Angle side angle means I'll use the law of sines. Just a ratio of sine over side. Always start with a known pair. I know this angle and the opposite side, so the sine of 38 degrees over 22 equals. And I want this side, so I'll use its opposite angle, the sine of 40 degrees over x. We just cross multiply and then divide. 22 times the sine of 40 degrees equals x times the sine of 38 degrees. And we're getting x by itself, so I'll divide it by the thing it's multiplied by on both sides. It's multiplied by the sine of 38, so I'll divide by the sine of 38 on both sides. No, I'm not just dividing by 38. 38 is an angle, and it's inside that sine function. But that represents some ratio between two sides that we just divide that ratio away, and you'll be left with just x there. So x is 22 times the sine of 40 degrees over the sine of 38 degrees. While you could type that in your calculator and get an approximation, I didn't ask for that on this test. I just want an exact expression. I believe you can use your calculator and type that in. Okay, now on this one we see that we have a right angle, which means our right triangle tools are available, being Pythag and the trig ratios. Given that I know two sides, I can get the third side using Pythag. Remember, that's leg squared plus leg squared equals hypotenuse squared. So the x will be on the same side of the equals as the 9. Square the 9 and the 15. Subtract 81 from both sides. And square root both sides. So x is a clean 12. And you may have recognized that this was actually a Pythagorean triple from the start. It's the 3, 4, 5 triangle just scaled up by a multiple of 3. So 3 times 3 is 9, 4 times 3 is this 12 we just found, and 5 times 3 is 15. So if you recognize the Pythagorean triple there, then you could just get 12 from the start, but Pythag works there quick enough. Okay. Number 7, again, we have a right triangle. So I'm not using law of sines, I'm not using law of cosines, those are for obliques. I'm using trig ratios or Pythagorean theorem. In this case, I'm using a trig ratio because I know two sides and I want an angle. Anytime you're going between angles and sides on right triangle, that's trig ratios. So from this angles perspective, that's the opposite. This is the adjacent, and that's the height. Remember, for trig ratios, you always label your HOA. Then you eliminate the one you're not using. Here I have 14 and 20, so I'm not using this one. You pick your recipe. Adjacent and hypotenuse is cosine. Set up your equation. Angle always goes inside the trig function. Adjacent over hypotenuse. And finally, you solve. I don't need to cross multiply or divide by anything here. I'm trying to solve for theta. Right now, theta is inside cosine, so to get rid of cosine or to undo cosine, I do cosine inverse of both sides. It's the function that undoes cosine. So theta is equal to the cosine inverse of 14/20. Okay, you could say trig ratio or inverse trig function. All right, for number 8, again, we have a right angle, so it's a right triangle. I'm not dealing with any acute angles, so no trig ratios or trig functions. But I am dealing with all sides, so I should be thinking Pythag. And if you do the Pythagorean theorem here, you'd be A-okay. But I also see a root 3 in the hypotenuse, and to me that's signaling a special right triangle. We know that the root 3 is one of the ratios in a 30, 60, 90 triangle. So if this is 30, 60, 90, that's the hypotenuse. And this could be the little leg. But if it was the little leg, I know the ratio between hypotenuse and the shortest leg is 2, or 1/2. And 12 is not half of 8 root 3. So if this is a 30, 60, 90, that'd be the big leg. And that would leave x for the little leg. Okay, our connecting numbers for a 30, 60, 90 are 2 and root 3. So if it is 30, 60, 90, this would be hypotenuse divided by 2 to get little leg. And 8 root 3 divided by 2 is just 4 root 3. Of course, 4 root 3 times root 3 should give me 12 if it's a 30, 60, 90. 4 root 3 times root 3 is 4 root 9. Of course, the square root of 9 is just 3, so that's 4 times 3, or 12. It does equal 12. So it looks like this does fulfill my 30, 60, 90. X must be 4 root 3. Okay, that's just a special right triangle. Again, if you do Pythag, you'll get the same thing. Number 9, I do not know if this is a right triangle. I have all 3 sides, though, so I can use Pythag to check, just like that very first question asked about. 12 squared would be my hypotenuse, if this is right. Or 12 would be my hypotenuse. And so 11 squared plus 10 squared will be equal to 144, 12 squared, if it's a right triangle. It's definitely not equal, so I know this is definitely not a right triangle. It's oblique, so I'll use the law of sines or law of cosines. Knowing all 3 sides, this is a law of cosine situation. In particular, when you're finding an angle, this is the cosine inverse version of it. And you always put the side opposite the angle you're finding first, and then the rest is just the other two sides. So 10 squared minus 11 squared, negative 2, don't lose that negative, times 10 times 11. And again, you can type that in the calculator. I believe you can, but I really just needed that expression there. Okay, for number 10, that's a right triangle again, and I've got an angle and a side. That's a perfect setup for your trig ratios. From the perspective of this angle up here, 22 is the opposite, x is the adjacent, and this is the hypotenuse. I know a lot of people like to find this angle and base it off of that acute angle, and that's fine, you can, but trig ratios will work from either acute angle's perspective. So once you label the HOA, you scratch out the one you're not using, leaving us with O and A. Pick the recipe, that'd be tangent. Set up the equation. The angle always goes inside the trig function. Opposite over adjacent. And then we cross multiply and divide. I'll make this a proportion. Put that over 1. Cross multiply, so I get 22 equals x times the tangent of 74 degrees, and then I'll divide both sides by the tangent of 74 degrees to get x by itself. Okay, so x is equal to 22 divided by the tangent of 74 degrees. Again, type that in the calculator if you like. I don't need an approximation here. That expression is perfect. Number 11 is just like the marathon question we had in class, just like the water slide question from the homework in that lesson. You've got two things of differing heights. So this flagpole is, let's see, 12 meters tall, and this one is 27 meters tall. Don't need to spend a lot of time giving too much detail here. Just want to get the measurements in the right place. We see they're 20 meters apart, and we want to find the angle of depression from the top of the taller one down to the top of the shorter one. Now, the common error is to put your angle right there from the top to the bottom. But we know an angle of elevation and depression are always between a horizon and the line of sight. So you have to imagine that from this pole, you were looking parallel to the horizon, and then your gaze was turned downwards towards this line of sight. That's your angle of depression. And you know that in any diagram like this, the angle of depression should always be congruent to the angle of elevation from the lower object's perspective upwards. So this is not theta. Theta would be here or up there. Because the shorter one is 12 meters tall and the taller one is 27 meters tall, that means that this height is the difference of those. This height here is 15 meters. And height is always measured perpendicularly, which gives us a right angle. Let's redraw the simpler right triangle to see what we're working with. We've got a bottom leg of 20 meters, that this height is 15 meters, and we're trying to find theta. Okay, this is a trig ratio situation because it's a right triangle. Don't try to use law of sines or law of cosines, just label your HOA. Scratch out the one you don't need. Pick your recipe. O and A is tangent. Set up your equation. Angle goes inside. O over A. And then solve, just like number 7. We're going to use the inverse trig function on both sides to break the angle out of that. So theta is the tangent inverse of 15 over 20. I did say that you can approximate this one because it's a modeling situation, so I think that's appropriate. The tangent inverse of 15 over 20 is about 36.9 feet. I'm sorry, 36.9 degrees. It's an angle. For number 12, you've got a lighthouse. Don't need too much detail there. There's the ocean, and we got some boat here. Okay. Now we have a lighthouse 55 meters high. And an angle of depression again down to this ship. So again, you'll be tempted to put the angle of depression right here, but we know that the angle of depression is always from a horizontal turning downwards, so it'd be from here down to there is the 18 degrees. And of course, that'll be the same as the angle of elevation. It's a right angle because of height, so it's asking the distance from the base. It's asking for this side here. We've got a right triangle again. Right angle, 55 meters, x, and 18 degrees. Right triangles don't use law of sines or law of cosines. Just use your trig ratios. Label your HOA. Scratch out the one you're not using. O and A leaves us with tangent for our recipe. Set up your equation. Angles always go inside trig functions. O over A. And this works a lot like number 10, where I'm going to cross multiply, and then I'll divide both sides by the tangent of 80. So you get x equals 55 over the tangent of, 18. I said 80. Tangent of 18. Once again, in a modeling situation, it's appropriate to approximate this. About 169.3 meters. Okay, on to the last page here. Just 4 triangles to solve. And when we solve, we're not just finding one measure, we're finding all unknown side lengths and all unknown angle measures. Because you always have to be given 3 things to solve a triangle, that means there's 3 things to find on each one of these. Remember, you always need to ask first, is this a right triangle? And if so, then you're using Pythag and trig ratios. If not, you're using the law of sines or law of cosines. Right here, I've got 3 sides. Let me check to see if it's a right triangle by using Pythag. The longest side is 18, so that would be the hypotenuse if it is a right triangle. Notice it does not fulfill Pythagorean Theorem, so it's oblique. Using that flowchart, you know an oblique with all 3 sides known means you should use the law of cosines. Okay, so let's start with angle A. To find an angle with the law of cosines, that's the inverse format of it. Always start with the opposite side from the angle you're finding, and then the other 2 sides. Okay, just got to have that formula memorized. Really, you could do the same thing for B and C, but I'll do the same thing for one of those angles and then triangle sum theorem. Just a little quicker though. There's 18 squared minus 8 squared. -2. I see that negative missing a lot. Make sure you get the negative on that too. So A is about 32.09 degrees. Of course, for B, you can do the same thing. Just make sure for B, you're now putting the 18 first, because that's the side opposite angle B. I'm going to go up and grab that expression I just did in the calculator and just change around some numbers. So I'll turn that 18 into a 12. 12 and make that the 18. Okay, so B is about 127.17. And I could do the same thing for C again, but instead I'll just do that C is about equal to 180 minus the other two. So about 20.7. Okay, that's all three unknown angles there, and we already had the three sides, so that triangle is solved. Number 14, again, I know that the largest angle here is 105 degrees. We saw this earlier on the test. That guarantees that this is not a right triangle. So I'll use law of sines or law of cosines. Let me just label what I know here. Okay, with a known angle and opposite side pair, that's perfect for law of sines. And on your flowchart, you see that the angle side case means you use law of sines anyway. Now, knowing two angles, quick triangle sum theorem will give me the third angle. That is 180 minus 105 minus 50. So angle A must measure 25 degrees. Okay, so for your law of sines, you just set up one big proportion. I'll start with my known pair. Sine of 105 over 25 equals sine of the next angle. How about the 25 degrees over the opposite side, A, equals sine of the other angle, 50 degrees, over the opposite side, B. And so I'll just do those two fractions, cross multiply and divide to solve for A, and then I'll do the first and the third fraction, cross multiply and divide to solve for B. Okay, so cross multiply here, you get A times the sine of 105 degrees equals 25 times the sine of 25 degrees, and divide both sides by the sine of 105, you get A equals 25 times the sine of 25 degrees over the sine of 105 degrees. And you can type that in your calculator and approximate. And then for B, you'll actually get the same thing, because you'll cross multiply the same thing except this angle changes. You'll cross multiply 105 times B, so it'll be like that, but with B. And that's going to be sine of 50 times 25, so it's almost the same, but that's a 50 there. And then you divide by the sine of 105. So B, you get pretty much the same thing, just a 50 degree there. And we already found that angle there. So that's all three unknowns found. That triangle is solved. Okay, number 15, a very common error here is to just get in a rhythm of oblique triangles and solve using law of cosines or sines again. But remember, if you check if it's a right triangle first, that'll make things a lot easier. The would-be hypotenuse is 34 there. So 34 squared is 1156. Let me see if the two shorter sides squared and summed equals that. And they do. So a squared plus b squared does equal c squared. This is a right triangle. Therefore, the longest side, c, must be opposite the largest angle, the right angle. Just like that, I know that c must measure 90 degrees. So there's only two more measures to find, and I can use trig ratios to do so. So let's take the perspective of angle A, for example. From A's perspective, and you can pick which one you want, which two sides you want to use. But let's say I want to use the 16 and the 34, then that would be the opposite from A, and the hypotenuse. Opposite and hypotenuse is sine. So the sine of angle A equals the opposite of A, 16, over the hypotenuse, 34. And then, as we saw previously, you just inverse sine both sides. So A is the sine inverse of 16/34. Similarly for B, you can just pick which two sides you want to use. and do a trig ratio, or I could approximate A here. The sine inverse of 16 over 34 is about 28.07 degrees. And then I can use a triangle sum theorem because I already know the 90. So 180 minus 90 minus the angle I just got for A leaves me with about 61.93 degrees for B. Okay, and then for the last question here, we have the angle side case. That is a triangle where we know an angle that is not between the two sides that we know. Of course, if you know the angle between the two sides you know, then that's a law of cosine situation. But you'll recall from your flowchart that in this situation, you have to use the law of sines to get an angle. We never want to use the law of sines to get an angle unless we're in this exact situation, because this will create the ambiguous case where you may have a second triangle that fulfills the given criteria. So we'll have to be sure to check for that after we do our law of sines. Okay, we do have this known pair, 42 and 5, so we'll start with that in our law of sines. And then we have this side B, we can get angle B using law of sines. So sine of angle B over side B, which is 6. Cross multiply. 5 times the sine of B equals 6 times the sine of 42 degrees. Divide both sides by 5. Sine of B equals 6 times the sine of 42 degrees, all over 5. And then you inverse sine both sides. So B is equal to the sine inverse of 6 times the sine of 42 degrees over 5. I am going to type this in the calculator and approximate it. I get approximately 53.41 degrees. Now, as I said, this is the ambiguous case. So I'm going to call that the first possibility for angle B. And we have to sort of split it into those parallel universes, where there's another answer to this question of the inverse sine that would also fulfill the given criteria. Recall, to get that other possibility, you do the supplement of this possibility. 180 minus what we just got. It's about 126.59. Okay, the following steps will be the same on each side of the, I guess, our solution here, on each possible triangle here. So we need to get the last angle. We already know angle A is 42, and we have a possibility for angle B. So we just do the triangle sum theorem. 180 minus angle B minus angle A leaves us 84.59 for angle C. Or in this possible universe, we have 180 minus angle B, that 126, minus the 42 for angle A, leaves us with about 11.41. The last thing to find is the length of side C, and we can use law of sines or law of cosines. Haven't used law of cosines to find the length on this test yet, so I'll do so now. Side C is equal to the square root of, looks a lot like Pythag at first, it's 5 squared and 6 squared, minus 2 times 5 times 6 times the cosine of the angle opposite the side you're finding, which we just said was about 84.59. Okay, that's the square root of 5 squared plus 6 squared minus 2 times 5 times 6 times the cosine of about 84.59. So about 7.44. And then on the other side, it'll be the exact same steps for this side too, except instead of this angle being 84.59, it's 11.41 in this solution. Still 5 squared plus 6 squared minus 2 times 5 times 6 times the cosine, but now it's 11.41 degrees. So about 1.48. So there you have it. We've got this triangle solved with both possibilities. And that is the Chapter 8 test. Email me with any questions you may have, and good luck studying.